quote from Professor Carlos Frank, Durham University: "I've spent my whole life developing a particular theory of the universe, and now that theory is being challenged. I welcome that because that's how we move forward. That's how we make progress in science." James Webb is overturning pretty much everything in cosmology that has been held as truth for 100 years. A new ultra-deep image shows again that we have made mistakes in astronomy. The telescope that was supposed to show us the first stars of the universe is becoming a killer of the previous worldview and may bring us a whole new science. Not all researchers are shivering in fear at the new facts. Many scientists welcome the developments because it has long been clear that something was wrong with our old theories. The discrepancies in the measurement of the expansion rate of the universe alone should have shaken researchers awake years ago, but instead of interpreting the warnings correctly, they clung to old theories. The cosmic microwave background radiation, or CMB for short, is considered to be the oldest light in the universe. The CMB was created around 380,000 years after the Big Bang, when the universe had cooled down enough for electrons and protons to form stable hydrogen atoms. Researchers call this transition reionization, and this change made the universe permeable to light. The CMB was first discovered in 1964 by the American physicists Arno Penzias and Robert Wilson. While the two scientists were working on a new type of antenna technology, they came across a constant noise coming from every direction in the sky. This discovery was long regarded as one of the strongest pieces of evidence for the Big Bang theory. Penzias and Wilson shared a Nobel Prize and went down in the history of astrophysics. The CMB very probably offers a snapshot of the young universe. Tiny temperature fluctuations are important sources of information about the conditions in the universe shortly after the Big Bang. Scientists use the CMB as a reliable imprint of the basic metrics of the material cosmos to measure the expansion rate of the universe, among other things. The astronomer Edwin Hubble had already made this calculation in the late 1920s. Hubble had discovered that distant galaxies move away from us in all directions and that their speed is proportional to their distance. Today, we know these observations as the Hubble law or the Hubble constant. Of course, Hubble did not yet have such good measuring techniques as were used decades later. When the CMB was discovered, researchers recalculated the rate, and the new value was significantly lower than the figure Hubble came up with. Later, scientists recalculated the rate again with Type 1a supernovae as standard candles. Astronomers had such stable light available that this light could be used as a kind of reliable measuring point. The distance is calculated with standard candles by comparing the observed brightness with their actual luminosity. The measurements within the CMB yielded an expansion rate of about 67 kilometers per second per megaparsec, while the measurements using the supernovae yielded about 74 kilometers per second per megaparsec. What does this really tell us? Did you know that this difference in determining the expansion rate of the universe has been known since the 1990s? Since then, researchers have known, or rather suspected, that something could be wrong with the assessment of the CMB, the measurement methods, or the idea of the expansion of the universe. The discrepancy between the various measured values of the expansion rate of the universe is known in science as the S8 tension or Hubble tension. The implications of this tension are not just any difference in measurement. The different results show us that profound things about how we have understood the universe so far are flawed. For a long time, researchers were at a loss. Since the James Webb Space Telescope went into service, the telescope has given scientists some surprises that may now shed light on the problem of the expansion rate of the universe. Galaxies so old and so mature that their formation must theoretically predate the Big Bang are completely overturning the old science in astrophysics. There is no longer talk of discrepancies or differences in measurement. Researchers are talking about the biggest crisis in modern astronomy. Not only could the rate of expansion of the universe be wrong, but the whole idea of expansion or the Big Bang is being put to the test. We see in Webb's images evidence of a universe that is very different from what we have long thought. The S8 tension was a first warning, and all researchers who still believed in the old theories now have a problem. Do we really know nothing about the universe? These days, many scientists are standing on the shambles of their life's work. They look into space in horror and no longer understand what they are seeing. In view of the crisis in science, we have to ask ourselves, what do we really know about the universe? To answer this question, we need to understand how science works. Theoretical scientists use a complex web of mathematical models, empirical data, and deductive reasoning to draw conclusions from the general to the specific. Their knowledge comes from a combination of observed phenomena, experimental results, and many theoretical analyses. The word theory alone shows us that these are constructs and ideas, but not truths. The only practical knowledge we have are the images that telescopes provide us with, the sound waves and radiation that we can capture with radio telescopes, and the latest data that neutrino measuring systems or gravitational wave detectors bring us. With the James Webb Space Telescope, we now have an instrument at our disposal with which we can, for the first time, break down the oldest light into individual frequencies and analyze it in a way that has never been possible before. Webb can show us which elements were predominant in galaxies over 13 billion years ago, how much mass was contained, and how many stars this indicates. The telescope can reconstruct the shape and direction of movement of a galaxy. But Webb can also have weaknesses. In some images, for example, the telescope cannot determine with certainty whether we are really seeing galaxies or black holes that shine just as brightly as a galaxy due to huge accretion disks. We have to face the fact that our science has long developed in a way that has accepted too many eventualities as truths and has long disregarded alternative explanations. Research has long been certain that it is right. The latest findings from the James Webb Telescope are important clues to replace theories with new truths, as has happened dozens of times in science. Scientists are currently waiting. The new discoveries are too crazy, and it seems impossible for many researchers to come up with new explanations right now. The new findings are shaking the foundations of our physics, and that scares many researchers. The teachings of physics today are still largely based on Isaac Newton's teachings, who conducted research in the 17th century. For centuries, his laws of motion and gravity were the foundation of physical understanding of the real world, including the universe. Newton's laws explain the movements of objects under everyday conditions and work quite well on Earth. In space, however, his ideas had to be extended, and this was largely done by Albert Einstein at the beginning of the 20th century. His special theory of relativity was published in 1905 and revolutionized the understanding of space and time. Einstein proved that space and time are relative to each other and depend on the movement of the observer. The general theory of relativity followed in 1915 and extended the concept with mathematical proofs of gravitational phenomena based on the curvature of space-time by masses, such as stars or galaxies. Einstein's laws and ideas were coherent in many areas, but he also reached his limits. The researcher knew during his lifetime that his theories would never be sufficient to describe the universe as a whole. He dreamed of finding the world formula, but he did not succeed. Incidentally, no other researcher has succeeded to this day. Where is the mistake? Wouldn't it be interesting to know where the mistake lies? Michio Kaku, the popular astroscientist from the USA, said in an interview that the person who solves this problem is sure to win a Nobel Prize. Let's see what fact scientists may have overlooked. Where have they possibly misinterpreted phenomena? Or are our telescopes to blame? At the top of the list of suspects for the real causes of the cosmological crisis are dark matter and dark energy. Our current models of the universe include concepts that dark matter and dark energy together make up about 95% of the universe. However, neither has ever been directly observed, and consequently, their real existence has never been proven either. They may not exist at all, and we have to explain the expansion of the universe and the dynamics in galaxies differently. Or perhaps both have properties that we do not yet know of. One idea, currently under discussion, is that the physical properties of the two dark components have changed over time, which could even mean that we are dealing with some kind of intelligence. The next thing to be put to the test is gravity. This force, which supposedly leads to attraction through mass or curvature in space-time through mass, has not yet been proven. The ideas of space-time curvature originate largely from Einstein and have been proven true many times over. However, we cannot currently rule out the possibility that gravity has completely different properties than we thought, or that it's a different effect that causes the gravitational pull on and between objects. Over the decades, a number of values have been established in our cosmology and astrophysics as so-called cosmic constants. These are values that are largely reliable because they hardly change. Calculations have shown that small variations of these alleged constants bring new momentum into the universe, and that we could explain a number of phenomena without the existence of dark energy. It is also possible that our interpretations of the redshift of light are wrong, and that, for decades, we have measured incorrect distances within the cosmos and also incorrectly determined the age of galaxies. Perhaps our assumptions about the initial conditions of the universe were also incorrect. We may have misinterpreted the cosmic microwave background radiation, and it's also possible that the universe cannot be traced back to a single starting point. This would mean that the idea of the Big Bang is wrong. Although we are technologically advanced, we cannot rule out minor errors in the Webb telescope or other observational instruments. Engineers and scientists admitted in the face of the crisis that errors in instrumentation, data processing, or interpretation are always possible. Subscribe now and never miss an exciting new video.